The real problem with having a science highlight talk right at the end of the CEDAR meeting is if you're a weak-willed individual like myself, you just can't resist showing some of these things in the earlier sessions, so I apologise if some of you have seen some of these results earlier. I'm actually going to preempt the rest of the talk with this slide here. I normally like to, sort of build up to a nice result at the end and reveal the answer at the end, but I'm going to show you really the main story right at the start here, so you can see where we're going. And what I'm going to do, I'm going to show some results from a new array of wind imaging instruments in Alaska. We've been doing wind imaging for years, but we've now got a 3-instrument array, and that's been operating in conjunction with the PINO campaign where we've been combining observations from Pfizer and SuperDARN and a bunch of other instruments, images and things, to try and get some sort of an integrated picture of what's going on with ion-neutral coupling in the auroral zone. So in this image here, I'll start with the yellow arrows. They are ion velocity vectors measured by SuperDARN, and you can see this beautiful westward jet running along here, a strong vortex or shear region here seen by SuperDARN. On top of that, the blue arrows are showing ion velocities measured by the Pfizer radar. You can already see how nicely they line up, and it's, I don't think there's been all that many maps where those two are plonked on top of each other. They agree very nicely. The white arrows are neutral winds measured by this Fabry-Perot array. And the really nice thing from that is, when I first looked at this, I thought, I don't know if that vortex is real or not, but you can see that it almost certainly is, because it's driven by this ion motion here, which has got the big vortex motion there, and the neutrals are following it just beautifully along there. In the background, there's an image. The green is showing auroral luminosity at 5577, measured by Don Hampton's all-sky cameras at Toolik Lake and at Poker Flat. And you can see that jet is beautifully coincident with where the aurora is located. And then finally, the blue through red colours are taken from the Fabry-Perot data. They're showing 5577 Doppler temperature, and basically this red band here is indicating a region where the auroral precipitation is soft. So, and again, that red band is coincident with the jet of neutral wind, and coincident with the ion vectors. So, a beautiful result. My purpose now is to go back and sort of explain where all that came from. So briefly, we've got this new array of wind images. We've had the instrument at Harp and Poker Flat for a number of years now. In the fall of 2012, we installed an instrument at Toolik Lake, giving us 3, and then soon we'll have another one at Kaktovik, giving us 4. Really nice coverage there. Now, a major theme I've noticed in my little sub-discipline of CEDAR this year is this idea of combining ground-based wind imaging instruments together to produce multi-static arrays. And lots of people in our field are doing this, and so this is just one example of that, and I think it really is the way forward for us. And the other part of all this is the PINO initiative, which has allowed us to bring all these data together. So this is, really is integrative aeronomy. I'm going to skip this, except to say this is what the raw data from one of these wind images looks like. These are, in this case, it's 261 spectra mapped across the sky. Many people ask me what these instruments look like. This is just a quick picture of the new Toolik Lake Fabry-Perot. I'll skip over that. All right, I do want to stop briefly on this slide. I put this together as a summary of, we had 2 PINO campaigns. We had a PINO campaign in November of 2012 and another one in March. And this is a summary of the November period. You can see we had several storms during that period with the F10.7 index shown here. Mostly I put this together to show the storm responses that we saw, but the thing I want to highlight here today is that there's always discussion in our community of how good our empirical models are. In the background here, I've got a brown curve which is obtained by running MSIS with these inputs for that period, and then superimposed on top of that in blue, green and red are the F region neutral temperatures measured by the 3 Fabry-Perots at their respective locations. And I don't know what people think corresponds to good or bad agreement between empirical models and data, but to me, I think this is really good agreement. And the really nice thing is that it's mostly really good agreement, but when we've got storms, it's not quite perfect, so you've still got a reason to go and actually measure it. You don't have to just run the model. This is the March period. Same story again, just beautiful agreement, really, between MSIS and the observations. All right, so I'm going to jump forward to a movie here. I'll just get the first frame going, and then I'll pause it if I can. It's a bit pixelated, I'm afraid. The resolution isn't as high as I'd like. Yellow arrows are SuperDARN, white arrows are the winds. Images in the background as shown, as I described before. The thing I want you to watch on this is, as you'll see the yellow arrows waxing and waning in strength as the ion convection builds and decays and builds and decays. And I want you to watch how closely and how quickly the neutrals respond. This is just monostatic data from one site because it was cloudy, but there's the convection waning, it's building up again, it's dropping down, and you see the winds just going with it, with a few minutes time resolution. Now I'll have to stop shortly because it got cloudy later this night, but just here's Pfizer coming in. What you'll see in a minute, you'll see Pfizer starting to turn, the convection starting to turn, and you'll see the winds trying to respond or doing their best. They'll weaken up here in this northern region as the convection turns around. They don't quite get as far as before the clouds came in. The wind didn't completely reverse, but we know from other days, had we observed for longer, the wind would have eventually come around and followed that reversal in ion convection, but there is a lag, and that's exactly what you would expect. So, really close, rapid coupling. It's not always the case, it depends, it's very local time dependent, but this early evening sector, the coupling is surprisingly direct. All right, so I mostly want to talk about arrays. And the thing about an array is you have multiple instruments. And I want to refer back, years ago I used to do some work in oceanography, and I had a colleague, a crusty old oceanographer by the name of John Penrose, with a very dry sense of humour, and he liked to quote what he called Penrose's first law of observational science. I think probably many others have said the same thing, but I remember John saying it. And his first law says the following: it says you should never measure the same quantity more than once if you're in the business of observational science, because if you do, you're going to end up spending all your time explaining why you got different answers when you measured it more than once. So when you have an array of instruments with overlapping fields of view, that's exactly what you have. You have multiple measurements of the same thing. What I'm showing here, I've got 4 frames, I'll just focus on this one. I'm showing the 3 Fabry-Perot instruments data analysed monostatically and independently. So the pink arrows are from Toolik Lake, analysed purely independently. The blue arrows are from Poker Flat, processed purely independently. And the orange arrows are from the Harp site, again, all processed independently. Now you can see that the agreement isn't perfect, but it's pretty darn good. Or at least to my eye, if I just zoom out so that we've got these other frames here, and it's the same story throughout, and it's the same story on multiple nights. I can't overemphasize how important just this simple repetition of measurements is, how much confidence it gives you in the results you're seeing. Even before we start trying to combine them together and produce a better product than just the individual instruments, seeing that the agreement between them is really quite powerful. There are places down here where they don't agree, and that would lead you to believe that you should try and do something better to combine the data together. So this is an algorithm that my former postdoc Callum Anderson put together. If you've got overlapping fields of view with a Doppler instrument, you can combine those different lines of sight and calculate the vector components directly. That's what's done here with those 3, the data from the 3 sites. Now the trouble with this algorithm works nicely. It gives you the most direct vector you can get by just doing that direct trigonometric recovery. The problem is there's only a limited region in which you can from which you've got suitable geometry to do that, but it is the most direct version of the analysis you can do. So this is the same data as I showed before, but now processed using this direct bistatic technique. We'd like to do a little. Just before I go on, I'll just by the way say that these monostatic results, some compilation of them into dial plots, the bistatic results and time series. These things are all available. At least when it's dark and the instruments are running, these things are all available in real time with a latency of 2 or 3 minutes or something like that. So, this stuff is coming out on the web. Anyone can see it in near real time. I'm not going to really say much about this other than to say that the way around that limited coverage that you get from the direct merging of lines of sight is to fit some basis functions directly to the line of sight data. We use these polynomial basis functions in expansion for each of the 3 wind components, up to nth order. I'll show you some results calculated up to 3rd order. So I'm going to show you a movie of those results. Now, I don't watch TV in the US, but I know in Australia if they put on anything that might be a little bit worrying, they always put up one of these sorts of warnings in advance to say that people might be disturbed. In this case, I think computer modelers might be disturbed by what this video shows, because I'm going to try and zoom in a bit. it really shows just a tremendous amount of complexity here. What I've got here, again, yellow arrows are supernown ion convection. White arrows are the wind response. The wind response fitted with that polynomial expansion algorithm, so with complete coverage here. The orange arrows are the underlying, let's see if I can zoom in even a bit more. The orange arrows are the underlying direct biostatic results. You can see how nicely they line up. Pfizer will come in a minute, and then all the auroral stuff in the background. So just tremendously rich, tremendously complicated, and there's Pfizer coming in now, and very, very direct coupling between the ions and the neutrals. So when we got these results, Bill Bristow sent a famous email to Aaron. The title of the email he sent him was, "Hey Ridley, simulate this, buddy," and he's still working on it, because it really is a complicated thing to try and deal with from a modelling perspective. So just a couple more things here. I pulled out a couple of still frames. I won't dwell on these other than to say the algorithm that we fits gradients as well as the wind itself, and it fits those gradients locally in each location. So that gives you the possibility of mapping things like divergence and vorticity. The array we have is such that algorithm has the most trouble at the very north and south ends, and there's a few areas where we may be getting some artifacts, but certainly in the core region over Alaska, those gradients look really good. We're also fitting vertical wind only at very low resolution, so that almost certainly the vertical wind is much more structured than this, but we're at least capturing the low resolution. There's some downwelling here and some upwelling there. So with this algorithm, we can actually pull out some additional features. The last thing I want to draw your attention to is this big region of blue here. This is vorticity. Now, a couple of years ago, Miguel Larson was looking at some of our HEX results from TMA, a horizontal TMA trail we released across Alaska, and he looked at that and he said, that meridional gradient of zonal wind that you're seeing, he said, that if you look at that, that satisfies the condition for inertial instability. And inertial instability is an instability that arises if an air parcel is displaced across a shear, and the change in Coriolis force that it experiences as a result of that displacement across the shear, if that reinforces the displacement, then you get an unstable situation. If it produces a restoring force, it's stable. This blue pattern here easily satisfies the condition for inertial instability across the entire region of Alaska. It probably doesn't matter in the F region because viscosity, means that geostrophic balance isn't that important. But we know that these wind fields map down. So somewhere lower, but this is all F region stuff, but somewhere down in the E region, that instability might start to matter, and that becomes an important question, I think, whether the E region flow could be inertially unstable. So what I did, I'll just skip through here. This is going to be a repeat of the previous movie, exactly the same thing, except down in this region here, I've used green to highlight all times when the condition for inertial instability is satisfied. And you can see across here, and I've sort of modulated a little bit so you can see how strongly the instability might be, how strongly it violates the instability criterion. So you can see initially, all of Alaska, the flow was strongly inertially unstable. In the F region, it probably doesn't matter, but if it maps down to the E region, it almost certainly does. And then it becomes stable for a while, and that criterion is met in some regions and not in others. So I think this is a really nice, or something I really want to look at now, is to take the green line data, reconstruct the wind fields lower down. There's some issues with that, but we'll do the best we can, and then just see how this instability situation plays out down at 120 kilometres, where viscosity might not be able to stabilise the instability, and there might be the possibility of seeing some unstable flow. So I'm just going to finish here. Actually, one other slide, just to say that at least all the data from the individual sites published online with very short lag times. So this is a 1 month table. Every one of those things there is a link you can click on to get a plot. There's one of these columns has got ASCII data. You can actually download the ASCII data, and we even provide a reader routine, an ideal reader routine to read the ASCII data, so you can grab these data yourself. So conclusions. This year, looking around the meeting all week, I saw a whole lot of emphasis on people in the wind community thinking about multi-static arrays, both with what they already have and trying to build better arrays into the future. The Pinot campaign allowed us to take one of these existing arrays and add to it other data from FISA, from CEDAR, from cameras, and various other instruments we haven't even got to yet. And so this really is integrative aeronomy. I was stunned. You know, I've looked at these neutral winds for years. I was stunned once we started getting the higher spatial resolution you can get with the better reconstructions from the array, the broader coverage, and then superposing that on top of CEDAR. And I was just stunned by how strong and direct the coupling is that you see in the data. I wouldn't have predicted that. We're going to have one more instrument coming online very soon. And finally, you know, we're supposed to be thinking this meeting about how to implement our strategic plan. For me, being able to superimpose my data with data from other instruments gave me a completely new look at what we were seeing. And so I think, you know, one of our take-home messages from here is one of the ways to address this new plan is for us to just really work on our collaborations and put our data together and start to see things in a merged, integrated way rather than separate things. So rather than worrying about technical issues of how we study complexity, you know, we've already got lots of tools, so let's put them together. And that's it. Thank you.